Hey everybody, welcome back to the last lecture in our semester, last lecture in our book, chapter 16. So you've made it, you survived. Okay, so in this chapter we are going to be looking at oxidation and reduction reactions, more commonly referred to as redox reactions. And we're going to start a discussion first with talking about the end of the internal combustion engine, or is it? So if our cars don't run on gasoline, then what will fuel them? So new technologies include the use of fuel cells to power electric vehicles. And so the electric motor is powered by hydrogen, stored as compressed gas, and its only emission is water. So that's what's really nice about these cars. Now they're quiet, they're environmentally friendly, and they're currently available only on a limited basis, but they should become more available in the years to come. Now, fuel cell technology is based on the tendency of some elements to gain electrons. We know that the gaining of the electrons is usually the nonmetals. And, excuse me, and the tendency of some elements to lose electrons. And as far as losing them goes, that usually comes from the metals. Now, the most common type of fuel cell is the hydrogen-oxygen fuel cell. So that's the equation that I've got here shown for you. And it's based on the reaction between hydrogen and oxygen. So in this reaction, hydrogen and oxygen form covalent bonds with each other. A single covalent bond is a shared electron pair. You guys remember that? So they'll form, in terms of the Lewis structures, something like that. So two hydrogen gas molecules and an oxygen gas molecule. Now, since oxygen is more electronegative than hydrogen, the electron pair in the hydrogen-oxygen bond is unequally shared, and we know that this can be represented with a arrow, a dipole arrow, or some charges such as this overall. Now, this positive charge would sort of be on each one of the hydrogens, but since this molecule would be, if we were to look at it in half, it would be more positive on one side, the positive side, and then there'd be a negative side. And so in effect, because of this unequal sharing, that oxygen gets a larger portion of the electrons, then oxygen has more electrons in water than in elemental O2. So in this reaction, it's gained more electrons. And so if we look at it, right, again, they both have, the oxygen has an octet in both situations. This oxygen right here that I'm highlighting has two bonds that are two electrons, and then it has, so those four plus those two lone pair electrons is 8. In the water molecule, this oxygen also has the two electrons that it shares inside this double bond. So there's 4 electrons that are essentially belonging to it. Now the difference is that of those 8 electrons, they spend more time around the oxygen in this atom, or in this molecule, than they do in this molecule. Because oxygen can compete with the other oxygen for those electrons, and so they basically stay right in the middle between the two. But in the case of the water molecule, the electrons are much closer to the oxygen. And so in that sense, the oxygen has gained a few more electrons. And also, the hydrogen has lost some. If we go back and look at this hydrogen over here, they were sharing 2 electrons pretty evenly between themselves. And now this same hydrogen that's in the water molecule now doesn't really get those same 2 electrons anymore. And it doesn't really get the one that it had, even though that it was sharing with the other hydrogen. They both have 1 electron apiece. Hydrogen's electron is probably more close to oxygen in the water molecule. Okay, so in this typical reaction between hydrogen and oxygen, the oxygen gains the electrons directly from hydrogen atoms as the reaction proceeds. And so when we, in this hydrogen-oxygen fuel cell, when we separate the hydrogen and oxygen, forcing the electrons to move through a wire in order to get from the hydrogen to the oxygen, those moving electrons are what constitutes an electrical current. and that's used to power the electric motor of the fuel cell. So fuel cells use the electron gaining tendency of oxygen, the electron losing tendency of hydrogen, all to force electrons to move through a wire, creating the electricity that actually powers the car. So the definition of oxidation. One good definition, though not the most fundamental one, is simply the gaining of oxygen. So gaining of oxygen is a really good example or a really good definition of what oxidation is. Now there's a couple of different kinds of oxidation. There's slow oxidation, like the rust that's produced by the oxidation of iron. And there's a more rapid oxidation, such as the flame from the oxidation of carbon in natural gas. So in one example, rust develops slowly. In the other example, the oxidation and the electron transfer happens very, very quickly. Now, a fundamental definition of oxidation, so not maybe the most... So again, the gaining of oxygen, this is true, but it is not the only way to define oxidation reduction reactions. And in fact, there are often no oxygens present. So it's not a fundamental definition, but it is a good definition. A more fundamental one, though, is that oxidation is the loss of electrons. Why did I write gaining of oxidation there? I apologize for that. I was supposed to say the gaining of oxygen. My bad. Okay. Oxidation is the loss of electrons. Reduction is the gain of electrons. Hopefully you remember that from, I think it was chapter 7. So oxidation and reduction must happen together. If one substance loses electrons, then another substance has to gain those electrons. And so consider our hydrogen-oxygen fuel cell reaction again. Hydrogen's oxidized, making it the reducing agent. Substances such as hydrogen, which have a strong tendency to give up electrons, are good reducing agents. They tend to cause the reduction of other substances. Oxygen is reduced, making it the oxidizing agent. Substances like oxygen, which have a strong tendency to attract electrons, are good at oxidizing other substances, and they tend to cause that other substance to get oxidized. And so we call them good oxidizing, we say it's a good oxidizing agent. Now you can use oil rig or Leo, the lion, says Gur, to help remember what oxidation and reduction are in respect to the electron transfer. And then again, oxidizing agent is always going to be the thing that got reduced. And the reducing agent is going to be the substance that got oxidized. Now, in order to identify oxidation and reduction, we've come up with a couple of rules. And so we're going to go through these rules in order to track the electrons in chemical reactions. So in this scheme, which we're going to look at, it's kind of like bookkeeping for electrons. All shared electrons are assigned to the most electronegative elements. Then a number called the oxidation state, or the oxidation number, is computed for each element based on the number of electrons assigned to it. So don't confuse oxidation state with ionic charge. A substance need not be ionic to have an assigned oxidation state. So the easiest way to assign oxidation states is to follow the rules for assigning oxidation states. So we're going to go through these. Now, rules 1 through 5, as it says in this slide, are hierarchical, which means that we do them in order. Rule 1 trumps rules 2, and so on and so on. And when we get all the way down to rule 5, if there's any other rules that would apply before rule 5 does, then we would do those first. So these rules, and I'll give you some examples as we go so that we don't get confused here. So first off, let's talk about rule 1. The oxidation state of an atom in a free element is 0. So I'm going to write an equation here. I'm going to write the equation of zinc plus copper, 2 plus, This reaction is a redox reaction because we're going to get some exchange of electrons. And we get copper solid and zinc 2+. Now, let's assign oxidation states to any elements in this equation following the rules. So what we see here is rule number 1 says oxidation state of an element of an atom in a free element is 0. Well, a free element would be any atomic or molecular element. So in this case, we see zinc. Zinc is a free element here. So we'll assign this the oxidation number of 0. I also see copper on the product side is a free element. If we had CH4 plus O2 gives us CO2 and H2O, like that. And we were going to assign oxidation states here. Only one of these is a free element. The rest of them are actually compounds. The free element is oxygen, O2, and so we would assign the oxidation state of the oxygen to be 0 in that equation. Okay, rule number 2 says the oxidation state of a monoatomic ion is equal to its charge. So if there's any monoatomic ions, their oxidation number or state is just the charge number. So if we look at that top equation, CH4 plus 2 O2s, there's no ions in there, so this wouldn't apply. The rules wouldn't apply here. On this lower one, we do see some charges. We see that there's a 2 plus on the copper, so copper will be 2 plus, or plus 2 oxidation, and zinc will also be a plus 2 oxidation. So we're done with that one. Okay. So we'll come back and talk about let's talk about it now. So whenever we finish assigning oxidation numbers, then we can look at the equation and we can decide who was oxidized and who was reduced. And it's easy. All we do is we say, did your oxidation number go up or down? If your oxidation number increases, then you were oxidized. If your oxidation number decreases, then you were reduced. Zinc goes from 0 to 2 plus in this equation. 0 to 2 plus. That's an increase. So we would say then that zinc was oxidized. Therefore, zinc would be the reducing agent in this equation. Copper had an oxidation of 2 plus, and at the end it had an oxidation of 0. Let's just make sure we understand what that means. It's saying that once it gained some electrons, it was no longer positively charged. And I'm saying that though it doesn't necessarily mean that it had a positive charge on it. Again, some elements don't have to have charges on them in order to have oxidation numbers. What an oxidation number ends up being is a relative number of how many electrons you have in the molecule you're in. And so for monoatomic ions, this is exactly what it looks like. This copper is missing 2 electrons, and so when it gains them, it's going to be neutral. But when we see this other equation up here at the top, that's not always the case, where we can just say, oh, it's an ion, or it has this or that number of electrons. It's more that they're being shared, and it's kind of like accounting for how many we can count of the 8 that it's really sharing. And so you'll see when we do some more examples. Okay, but copper then was reduced. So copper went from being 2 plus to 0, so it was reduced, therefore it is the oxidizing agent. Let's keep going with our rules. Rule number 3 says, the sum of the oxidation states of all atoms in, and there's 2 cases, a neutral molecule, that would apply for CH4, CO2, H2O, or a polyatomic ion, is equal to the charge of the ion. Let me grab an example of a polyatomic ion that we can do together. Okay, let's see. Oh, okay, here we go. Oops. Just kidding. Your book doesn't have a lot of examples of polyatomic ions within these redox equations. Okay, so then what I'm going to do is just give us a molecule. Since we don't have an equation necessarily to use, that's okay. I don't need an equation. I can get by. Let's do copper 2 nitrate. So I'm actually going to do some erasing here. Okay. This is copper 2 nitrate. So let's say that we had this molecule in one of our reactions and we needed to write down all of the oxidation states for all of the atoms within this molecule. So rule number 3 tells us, right, because rule numbers 1 and 2 don't apply here. If we saw this in an equation, we would definitely not consider it to be a free element, and we would definitely not say that it's a monoatomic ion. So rule number 3 would say, all of the oxidation states of all of these atoms have to add up to the charges that these polyatomic ions would have. And what that means is, if you remember, CuNO3 is a copper 2 plus and 2 NO3 minuses. So what that means is, when I'm adding up together the oxidation states of the nitrogen and oxygens inside NO3 minus, they have to add up to a -1, because that's the charge of this overall molecule. Up here, in these examples, all of these add up to 0 because all of these are neutral molecules. And so we're just saying oxidation states are going to represent the overall charge at the end of this. Excuse me. So let's assign some oxidation states. Well, actually, that's just a rule. That's just a rule. So there's nothing actually to do here if that's just the rule. So let's we'll come back to this one down here because I want to show you how we actually apply the rules. Rule number 4. In their compounds, group 1 metals will have an oxidation state of +1. Group 2 metals will have an oxidation state of +2. So let's go back and look at our two equations. In our blue equation, are there any group 1 or group 2 metals? No. That would be like if we had a barium hydroxide in there or a sodium chloride, right? If we had a sodium chloride, let's do a sodium chloride. Let's say that we have Na solid plus Cl2 gas, and that this makes 2 NaCl solid. Let's assign some let's assign some oxidation numbers. Oxidation state of an atom in a free element is 0. Excellent. Sodium, free element. Chlorine, molecular element, also free element. That was easy. Number 2, oxidation state of a monoatomic ion. Well, we don't have any of those. Number 3 just says that NaCl has to, oxidation numbers have to add up to 0. Rule number 4 says my group 1 and group 2 metals will have the oxidation number equal to those column numbers. This is sodium. It's in column 1. So now I can just say, because sodium is a group 1 metal, in this compound, NaCl, sodium has a +1. Rule number 3 said that this molecule had to total to 0. So since I've already given sodium a +1, chlorine has to be -1. That's how we use these hierarchical rules. Now, if you notice this equation up in blue, up to the top here, CH4 plus 2 O2s, it doesn't have any group 1 or group 2 metals. There is no monoatomic ions. There is no polyatomic ions. There are no additional free elements in here. So we've run out of rules, essentially. Out of the 5 rules, we're down to the 5th rule that has to answer all of our ability to solve this. Let's look at Rule 5. Rule 5 says, in their compounds, nonmetals are assigned oxidation states according to this table. Entries at the top have priority over entries at the bottom. So if there's a fluorine, it's going to be -1. If there's a hydrogen, we'll also give it a -1. If there's an oxygen, it'll be a +2. I'm sorry, a -2. If there is and there's a typo here. Yeah, big time typo. Hydrogen is +1. Hydrogen is not -1. right? No. Hold on. I gotta check the book. I think there's a typo on this. I'm almost 100% sure. But seeing an incorrect graphic does something to your brain's confidence. All right, so I've just pulled up the rules inside your guys' textbook to give that a look real quick and see what it's going to say here. Yeah, hydrogen is +1, so I don't know how that typo happened, but I definitely am glad that we caught it. Okay, hydrogen's +1, oxygen's 2 minus, and so forth. Group 7, which is the halogens, will be -1. Group 6, which is where oxygen is, -2. Group 5, where nitrogen is, -3. Pretty much what their charges are in general. So let's go back and do those. So now we can fill in the oxidation numbers on our combustion reaction up here. So CH4, well, C wasn't even on that list of priorities. So hydrogen gets the priority. Hydrogen will get a +1. Therefore, there's 4 of them, so that's 4 +1s. So for this to be neutral or be 0 altogether, then carbon has to be -4. So carbon gets a -4 oxidation there. We look over here at CO2. Again, oxygen has the priority. Oxygen is going to be -2. There's 2 of them for a total of -4. So carbon will be +4. And then we see oxygen over here and hydrogen in water. Hydrogen, of course, has priority, +1. 2 of them, so +2. Oxygen will be -2. All right. And so now we can look through here and assign or decide who gets oxidized, who gets reduced. And this one's a tricky one. So if we take a look, we're going to see that carbon clearly got oxidized. Carbon went from being -4 to being +4. So it went up by 8. It gained 8 electrons and was oxidized, making it the reducing agent. Now, oxygen got reduced. And look at here, we have 4, right? 2 times 2 is 4 oxygens that are all 0. And now we have 2 oxygens and 2 more oxygens that are all -2. So oxygens went from 0 to -2, being reduced. Carbon went from -4 to +4, being oxidized. And that's how we would see who's the oxidizing agent, who's the reducing agent. Again, oxidizing agent would be oxygen because it got reduced. So let's come down here to finish the copper nitrate. So group 1 or group 2 metal, not present. What do we have here? We have that oxygen has priority, so -2. There's 3 of them. So within this parentheses, we've got a total of -6. But the inside of the parentheses only has to have a minus on the end of it. So we're not going to cancel out all of those -6s. We're only going to cancel out 5 of them. So that gives nitrogen a +5. Nitrogen's +5. Oxygen's -2. There's 3 of them. So overall, it's -1. We have 2 of those, 2 nitrates, and this whole thing needs to be neutral. So copper has to be 2+. And so just like that, we've assigned all of these atoms. And if this was part of a compound, then we could see what the oxidation or a reaction, we could see what the answer would be. We're going to try one, so let's do one. So you get out your table, or you have your rules in front of you with your book, and then we'll work through this. So first off, we're going to see free elements. So we see a free element here in calcium. We see a free element here in hydrogen. No monoatomic ions. So rule number 2 doesn't apply. Rule number 3 just says that for hydroxide here, OH minus, that's going to add up to -1. And that for water, we're going to have a neutral molecule. Well, for calcium hydroxide and for water, these things will total to 0. Rule number 4 says if we have any group 1 or group 2 metals, we have a calcium. Calcium is a group 2 metal. So calcium is going to get a 2 plus, which is good. We know that that's going to work with the hydroxide being minus. All right, so now we're at rule number 5. Rule number 5 says fluorine. I don't see any. Rule number 5 says hydrogen. Okay, so hydrogen is going to be +1. There's 2 hydrogens there, so oxygen in this molecule has to be -2. Over here, we see oxygen and hydrogen in this hydroxide. Hydrogen, again, with the priority, so +1. And then oxygen will have to be -2, not because of the rule that says oxygen is -2, but because of the rule that says hydroxide is -1. If hydrogen is already +1, then oxygen has to be -2. There are situations where oxygen might not be -2, but here it has to be. So now we can look at all the atoms and see if anything was oxidized or reduced. Off the top of my head, I see calcium did get oxidized. It increased its oxidation number. I look at the hydrogens, and I do see that hydrogen got reduced. At least some of them did. It looks like there's a total of 4 hydrogens, right? 4 hydrogen atoms. A couple of them, at least 2 of them, didn't change. So 2 of them are still +1, but 2 of them did change. 2 of them went down from +1 all the way to 0. And that makes sense. There's only 1 calcium. Calcium only gave up 2 electrons. There's only enough to give 2 electrons to 2 hydrogens, not to 4. So there's going to be some hydrogens that didn't change. But that's why we want to go through and assign oxidation numbers to everything. All right, now when you balance a redox reaction, you need to worry about, so let me say it this way. Redox reactions that occur in aqueous solutions are difficult to balance by inspection, and they require a special procedure called the half reaction method. In this procedure, the overall reaction is broken into 2 half reactions, one for oxidation and one for reduction. And the half reactions are balanced individually, and then they get added together, and that makes it actually a little easier. So first, let's look at the oxidation. So you assign oxidation numbers to all the atoms to be determined, so that you can determine, what is being oxidized and what is being reduced. And then you divide the reaction into the 2 half reactions, one for oxidation, one for reduction. So here, the oxidation side is just the aluminum and the aluminum. It's the 0 going to 3+. And then the reduction is just the silver atoms. It's the positive silver becoming neutral silver. And so you write those down as reactants and products. Just you keep them on their respective side of the arrow, that whatever side of the arrow they're on. And if it is the case that, as in this case, the half reactions are already balanced with respect to mass, meaning the number of each atom is the same on both sides, but that's not always the case. But this one isn't balanced with respect to charge. If you notice, the charge on one side of this reaction, especially here, 3+, doesn't balance the charge on the other side. And when we balance reactions, the charges need to be the same as well as the masses. So we need to balance them. And so the way that we do that is we can show the electrons. So what we're doing here is we're zeroing out both sides. So instead of there being just a 3+ shown, we're not just saying there's 3+, there's actually also 3 minuses that were liberated, and that should make sense. The aluminum is now an aluminum and some electrons, because it let some electrons go. Likewise, on the side of the reaction that has a positive charge, we're going to say that that's going to gain an electron. The electron is going to add to that positive charge. So by doing this, we're not just getting all of the electrons that we need to have charged neutral sides of our equation, but we're also making it make a little more sense, right? We said reduction was gaining electrons. So this is showing that electron being gained. We said oxidation was losing electrons. Well, this is showing how those electrons are being lost. Okay, so then once we've done that, we see if the electrons are the same in both of our equations. So right up here on the aluminum side, I see that aluminum is exchanging 3 electrons, or giving away 3 electrons to someone. But on the silver side, we see silver's only getting 1 electron. So something doesn't work here. They're not balanced with respect to each other. So we need to do something. And what we can do is we can actually multiply one or both of our half reactions by an appropriate whole number. In this case, we can multiply the bottom reaction, the reduction reaction, by 3. If we multiply it by 3, we see that now it is going to be 3 electrons and 3 silver ions that will react to form 3 silver solids. Now our electrons are equal. The number being given is the number being received. The numbers being exchanged are the same. And we can add them together. So our arrows just all line up. Everything on the reactant side just carries down. Everything on the product side carries down. And anything on opposite sides of the reaction in the 2 different half reactions can get canceled out. And so here you can see we can cross out the 3 electrons and the 3 electrons. There's no reason to mention them or to write them on both sides. So aluminum plus the 3 silvers will give us aluminum 3 plus and 3 silvers. So that's a balanced equation. Now, with the balancing, you always want to make sure that your atoms, again, are still matching up. So after we've added the half reactions together and canceled the electrons, we have to make sure all of our other atoms are balanced. And in some cases, we're not going to be able to balance them without adding a few other species. Now, as it says here, notice that the charge need not be 0 on both sides of this equation. It just has to be equal on both sides. So when we were doing our reaction, half reactions, we were trying to make the side of the reaction 0. We were trying to make it be 0. That's not the case with our overall reaction. But our overall reaction still has to have both sides of the equation equal to each other. Okay. Do I have an example for us to do? I think I have an example. Let's see. So this is the procedure for balancing the redox reaction in acidic solution using the half reaction method. And here's the basic method. Okay, so yeah, let's do a half reaction method. I'll pull one up from the book, and then we will just do it together. Now, I want you to pause this and look through the rules. I'm just going to go through it my way, but I'll explain what I'm doing along the way. I basically do everything here. We assign oxidation states, we separate the reactions, we balance it all, we add them together. I just don't necessarily do it in all of those same orders. Okay, so I'm finding a acid reaction for us to balance, and then maybe we'll also balance one in base. Okay, so let's do ClO4 minus, ClO4 minus plus Cl minus gives us ClO3 minus and chlorine gas. All right, so is there any free elements? Chlorine. Is there any monoatomic ions? Chlorine. Is there any group 1 or group 2 metals? No. So now we're on rule number 5, essentially. Rule number 5 says fluorine? No. Oxygens? Yes. So oxygen here is -2. Minus 2 times 3 is minus 6. But this thing needs to be minus 1 overall. So chlorine then has to be plus 5 in this molecule. And on the other side, we see same situation. Oxygen is minus 2. There's 4 of them. That's minus 8. This thing only needs to be minus 1 overall, so chlorine is plus 7. All right, let's see if we can figure out oxidized and reduced from this. So we see that there's a chlorine. They can't all reduce. So it looks like this chlorine goes from plus 7 to plus 5. So that's the reduction. And then this chlorine over here goes from minus 1 to 0. And that is going to be the oxidation. Now, right off the bat, you can see that there is an unbalance. We don't have enough chlorines to go around, and we don't have enough oxygens to go around. So that's where we're going to have to get into our half reactions and fix that. Okay, so let's get at our half reactions. So our first half reaction is going to be the reduction half reaction. So let's take ClO4 minus. Reduction means gaining electrons. It looks like it gains 2. Plus 2 electrons. And we get ClO3 minus. So there's our reduction side. Let's do our oxidation side. Oxidation-wise, we've got Cl minus turning into Cl2. So right off the bat, that doesn't make sense. So we're going to need 2 chlorines. 2 Cls becoming Cl2 makes perfect sense. And 2 Cls would have 2 extra electrons. So let's get rid of these 2 extra electrons. So there's the oxidation side. The 2 chlorines losing their 2 electrons to form a Cl2 gas. Now our electrons here are balanced, so we're good. So we don't have to multiply anything by 2 here. You see that we basically handled that by putting a 2 in front of the Cl. All right, so I'm going to then rewrite the top equation so I can show you how we're now going to balance it with respect to the oxygens. Because you probably noticed that there are some oxygens that are not the same numbers on both sides. And so that's what we're fixing when we fix this. So I'm going to write my equation out. So on the product side, we've got, so remember I can cancel this out when I add them together. So I've got ClO3 minus plus Cl2. And on the reaction side, I've got 2 Cl minus plus ClO4 minus. All right. So we need to get our chlorines in order, and we do. There's 3 on both sides. Now we need to get our oxygens in order. And you can see that we've got 4 on the reactant side and 3 on the product side. So this is easy. When we balance with acid or base, we get our oxygens in order by adding waters. So I'm going to add 1 water to the product side. So now my 3 oxygens plus the water makes 4 oxygens. And we call this balancing in acid because now I'm going to add acid to balance those hydrogens. There's 2 hydrogens there. So I'm going to add 2H plus. And that's it. That's the equation. So now, obviously, the only thing that's missing is our phases. That would be liquid. And that's it. 1 water, 2 hydrogen ions, and this is a balanced equation. This one wasn't hard, right? We just had to balance the O's and we had to balance the oxygens. I mean the chlorines. We'll do another one. We'll do a base one. So the only thing that's different with base is that after we've added, here's the base reaction. After we've done adding the water and then adding the hydrogen ion, then we neutralize the hydrogen ion by adding OHs to both sides. And so we end up with OHs at the end instead of hydrogen ions at the end. So let's do one of those. So I've got NO2 minus plus aluminum. Sorry, I'll put the phases. Gives us ammonia and aluminum oxide, or some kind of ionized aluminum oxide compound. Okay, so assign oxidation states. Free elements, so aluminum. Any monoatomic ions? No. Any group 1 or group 2 metals? No. Rule number 5 says hydrogens? Yes. +1. So 3 plus 3, so nitrogen is -3 in this neutral compound. All right, any other hydrogens? No. Oxygen, okay, so oxygens, -2. Now in this one, 2 oxygens is 2 minus 2s, so -4. Aluminum has to be +3 for this thing to be -1 overall. And on the other side, oxygen again, -2. There's 2 of them, so -4. Nitrogen has to be +3 for this to be -1 overall. So now we can see definitely oxidation and reduction. Nitrogen goes from +3 to -3. Let's just say it. It's -6 electrons. This is a reduction. I'm sorry, this is an oxidation. No, it's a reduction. It didn't -6 electrons, it gained 6 electrons. And aluminum. Aluminum was the oxidation. It went from 0 to +3. So it did lose 3 electrons. And this was the oxidation. So we've got our 2 half reactions. So let's write them out. So I've got NO2 minus. We said it's going to gain some electrons. It looks like each nitrogen here actually gains all 6 electrons. So there's not going to be, there's no need to have 2 nitrogens or anything like that. So we're just going to say plus 6 electrons is NH3. And then we'll go to the aluminum side. We'll say aluminum becomes aluminum AlO2 minus and 3 electrons, right? Because it goes from 0 to +3. So we can balance for electrons now by multiplying the bottom equation by 2. Because by 2, then we're going to get 2 aluminums. We're going to have 2 AlO2 minuses and 6 electrons. So I'm going to handle that. So 2 aluminums, 2 of those, 6 electrons. So we've multiplied that reaction by 2. Now we can cancel out our electrons and add this together. We're going to get NO2 minus plus 2 aluminums give us NH3 plus 2 AlO2 minuses. Okay, now we have some oxygens that need balancing and some hydrogens. So let's do the oxygens first. Actually, it looks like the oxygens, yeah, we need to, so you can see here we've got 2 of these AlO2s. That's 4 oxygens. And over here we only have one of these guys. We don't want to change the ratios of any of this stuff though. We just want to add waters because right now nitrogens are the same. If we start making, let's say, putting a 2 here, now we've got the right number of oxygens, but we'll have to put a 2 here to get the right number of nitrogens. Now we've got 6 hydrogens, and as soon as we put a water, we'll have more oxygens. So it kind of messes everything up. So I'm going to get rid of that 2 and this 2. We don't need a 2 there. So we'll add some waters. So, and why am I adding water? Well, because there's 4 oxygens on one side and only 2 on the other. So let's add 2 waters. So now we have four oxygens on both sides. There's the 2 in the water and the 2 from the NO2. So that's 4 altogether. 4O. Over here we have 2 of these AlO2s, so that's 4 O's. But now we have 3 hydrogens and 4 hydrogens. So we're missing 1 hydrogen on this side. So I'm going to add an acid molecule, an H+, like that. All right, so are we balanced? We are, but we're supposed to be doing this in base. So we can't have an acidic solution here. So we're going to need to go and add sodium hydroxide to both sides. Okay, sodium hydroxide to both sides, right, is going to have the effect of making one of these into a water. Okay, and so canceling that out as water, and then leaving hydroxide on the other side. We can now get rid of our 2 waters because we don't need 2 waters because 1 water on each side cancels each other out. Now let's just double check. Let's count everything. So I'm going to go through each one. So hydrogens, we've got 3, because there's a hydroxide also over here. So altogether we have 3 H's. 3 H's. O's, we've got 1, 2, 3, 4. 4. 1 nitrogen, 1 nitrogen, 2 aluminums, 2 aluminums. So the overall finished equation here, let's write it out, was H2O plus NO2 minus 2 aluminums and a hydroxide, ammonia, and 2 AlO2 minuses. So that's our balanced equation. Phases, that was a gas. That was aqueous, solid, aqueous, liquid. Balancing, if you're not good at balancing in general, then this will be a challenge, but that's how we do the balancing with the redox reactions. So it kind of combines everything. Okay. Let's talk about photosynthesis real quick. So photosynthesis, right, is what plants do. Solar energy reaches the Earth in the form of electromagnetic radiation. You guys remember that from, maybe that was chapter 7. So the wavelengths that make up visible light have an additional and very crucial role to play in the maintenance of life. Plants capture that light and use it to make energy-rich organic molecules, such as carbohydrates. So animals get their energy by eating plants or by eating other animals that have eaten plants. So ultimately, virtually all of the energy comes from sunlight. And so how is that energy captured? How is that sunlight captured and turned into useful energy or useful molecules that organisms can use and transfer? Well, it comes in the form of various oxidation and reduction reactions in our bodies. In respiration, Energy-rich molecules of glucose are burned in a reaction that can be summarized as follows. So in our bodies, we take glucose, we breathe oxygen, we have this reaction, this oxidation reaction takes place in our bodies, and carbon dioxide is formed. We oxidize all of the carbon in our glucose and sugar into carbon dioxide, and then we reduce all of the oxygen we breathe into water, and then this frees up energy. Well, photosynthesis is the series of reactions that plants use to capture sunlight, and it's kind of a backwards reaction, well, at least as far as a net reaction goes, backwards from respiration. There's a lot of different intermediates and steps that are required. It's not exactly just a backwards of the same process. But these oxidation and reduction reactions are what are used. Oxidation usually gives energy, reduction usually builds up molecules. And so, yeah, the key principle in photosynthesis is the reduction of carbon, and the key in the respiration in our bodies is the oxidation of carbon. All right, so let's talk about reactivity series. We did a lab on this. So the activity series of a metal lists the metals in order of decreasing tendency to lose electrons. So the metals at the top of this list have the highest tendency to lose electrons. These are the ones that are most easily oxidized, and they're the most reactive. The metals at the bottom of the list have the lowest tendency to lose electrons. They're the ones that are most difficult to oxidize, and they're the least reactive. And so each reaction in the activity series is an oxidation half reaction. The half reactions at the top are most likely to occur in the forward direction. The half reactions at the bottom are most likely to occur in the reverse direction. So if we pair a half reaction from the top of the list with anything, any of the reverse half reactions beneath it or on the bottom of the list, we get a spontaneous reaction. That's what spontaneous reactions are, elements that come into contact with each other that have different reactivities. Gold is very low on the activity series, so because it is very difficult to oxidize, it actually resists the tarnishing and corrosion that other metals see. Metals used for jewelry, such as silver and gold, are near the bottom of the list. They stay relatively inactive. When is a reaction spontaneous? Well, on the left here, I've got copper 2 plus. We see it oxidizes magnesium. In the middle, we see solid copper actually forms from the copper 2 plus and the magnesium. And on the right, we see that magnesium does not oxidize copper. So these two metals put together in different combinations only have a reaction one way. If we put a magnesium strip into copper, we do see a reaction. If we put a copper strip into magnesium, we do not see a reaction. And this has to do with the tendency to give away their electrons, right? Clearly, copper wants to gain electrons from magnesium and not the other way around. And so when we put these two together in that situation where magnesium's got electrons to give and copper's deficient, copper gets them and magnesium gave them away. But when we put these two guys together, when we have magnesium needing some electrons and copper holding the electrons, copper does not give them to magnesium. So these reaction series can be predicted by looking at those reactions on the list here. We can see magnesium giving away electrons, right, going from solid to not having electrons, is more likely to happen than copper doing the same thing. So that's why when we pair magnesium with copper 2 plus, we see a reaction. Now, we can also use this list to predict whether or not a metal will dissolve in acid. Most acids will dissolve metals by the reduction of hydrogen ions to hydrogen gas and the corresponding oxidation of that metal into its ion. Metals above the hydrogen gas reaction on the activity series will dissolve in acids, while metals below hydrogen, or H2, don't dissolve in acids. An important exception to this rule is nitric acid, which through a different reduction half reaction actually dissolves some of the metals below H2 in the activity series. So there are some acids, we can use different acids And again, because of the different reduction half reaction. But the half reaction that produces hydrogen gas, that uses hydrogen ions, usually like from, let's say, HCl producing, H plus and Cl minus. So HCl being the source of the hydrogen ions for this reaction, only works with metals above it on this list. So let's see if we can predict whether or not this metal will dissolve in acid. If we look at the reactions, we can see oxidation states, right? So we know direction. So this is oxidation. We know this is reduction. So as long as this oxidation of zinc is higher up on the list than the oxidation of H2, what I'm saying is, as long as zinc into zinc 2 plus and 2 electrons is higher on the list than hydrogen gas into 2 hydrogens and 2 electrons, then this will happen. Where is zinc? Right here. It is higher than the hydrogen, than the oxidation of hydrogen gas. Therefore, if we were to pair zinc with the backwards reaction, meaning zinc with hydrogen ions, this would be a spontaneous reaction. And that is the case. If we add these together, we see that this reaction does indeed dissolve that metal. Hydrogen ions from something like HCl will dissolve zinc, or zinc will dissolve in the acid. And again, higher tendency to oxidize, higher tendency to lose the electrons. Both of these guys face each other. One of them is going to lose their electrons. One is going to gain them. Higher on the list, you're going to lose your electrons. Hence, zinc loses its electrons and not the backwards direction where hydrogen loses its electrons. Okay, batteries. Electrical current is the flow of electrical charge. In this figure, electrons are flowing through a wire. Now, since redox reactions involve the transfer of electrons from one species to another, they can create electrical current. Electrochemical cells that create electrical current from spontaneous reactions are called voltaic cells or galvanic cells. In a voltaic cell, the following occurs. A solid strip of zinc is placed into a zinc 2 plus solution to form a half cell. Because remember, the half cell has the neutral species and the oxidized species, or the reduced species, but two versions of the same guy. So that's the half cell of the oxidation. A solid strip of copper is placed into a solution of copper 2 plus, forming our second half cell. Now the two half cells have to be connected by a wire attached from the zinc through a light bulb if we would like to see this electron transferring happening, but we don't need the light bulb. But as long as the wire connects the two and then connects to the copper, electrons can flow from one to the other. Now a salt bridge has to be there to complete the circuit. It allows the flow of ions between the two half cells. So we've got a salt bridge. So it needs to be a complete situation here. The natural tendency of zinc to be oxidized and the copper 2 plus to be reduced results in the flow of electrons through the wire. The flowing electrons constitute electrical current that lights the light bulb. Now, in a voltaic cell, the metal strip where the oxidation occurs is called the anode. And this is labeled with a negative sign. Oxidation being losing electrons, right? But it's also where the electrons are being generated. And since they're forming here, the electrons are starting here, we give it that negative sign. Now, the metal strip where the reduction occurs is called the cathode and is labeled with a positive sign. Electrons flow from the anode to the cathode, from negative to positive. So that should make sense. Rivers can be a good analogy for electrical current. We'll talk about non-spontaneous reactions in a second. In a voltaic cell, the electrical voltage is a driving force that causes the electrons to flow. A high voltage corresponds to a high driving force. Okay, while a low voltage is a low driving force. Electrons flowing through a wire are similar to water flowing in a river. The quantity of electrons that flow through that wire is analogous to the amount of water that flows in the river, or like the current. So the driving force that causes the electrons to flow through a wire, called potential difference or voltage, is analogous to the force of gravity that causes water to flow in a river. So a high voltage is analogous to a steeply descending stream bed. A low voltage would be a flat sort of slow-moving creek. Okay, so the voltage of a voltaic cell depends on the relative differences of the reactants to undergo oxidation and reduction. Combining the oxidation of a metal that's high on the activity series with a reduction of a metal that's low on that activity series will produce a battery with a really high voltage, or a relatively high voltage. For example, the oxidation of lithium solid with the reduction of copper 2+. These guys are opposites on that table, would be a really high voltage. Combining the oxidation of a metal on the activity series with the reduction of a metal just below it would give a low voltage. If there's not a big space between the two, then there's not a big driving force to get those electrons to the other one. Combining the oxidation of a metal on the activity series with the reduction of a metal that's above it doesn't produce a voltaic cell at all. In fact, you cannot make a voltaic cell by trying to oxidize copper and reduce lithium. It doesn't work. Such a reaction is non-spontaneous and does not produce an electrical current. So yeah, the direction, the reactants that you pick have to be in the correct positions on that reactivity series, or you'll just build a battery that doesn't work, essentially, or that works the wrong way. It'll flow in the other direction if you were to have built it that way. So let's understand why a dead battery happens. As the zinc in this copper 2+ voltaic cell is used, the zinc electrode dissolves away as the zinc is oxidized into zinc ions, right? Similarly, the solution is depleted of copper 2 ions as they deposit as solid copper. So the zinc that's supplying the electrons will eventually become all zinc 2+, and there won't be any zinc left. So that's when one part of this battery could go dead. The other part would be if there runs out of copper 2+. If every bit of copper 2+ in here gains electrons and becomes copper, then there's nowhere for electrons to go, and so the current stops. So once the zinc electrode is dissolved and the copper 2+ ions are depleted, the cell's dead. Some voltaic cells, such as those employed in the rechargeable battery industry, can be recharged by running electrical current from an external source in the opposite direction. This causes the regeneration of the reactants and allows repeated use of the battery. So again, the voltaic cell dies with extended use because the reactants, and those are in this case the zinc electrode and the copper 2+ solution, get depleted. And in this case, the zinc 2+ ions and the copper electrode or copper solid, they accumulate. And so when these guys accumulate to a certain point, the battery stops. When these guys go down, obviously the battery stops. Let's talk a little bit about dry cell batteries. So one of the most inexpensive type of dry cell battery is one composed of a zinc case that acts as an anode, and the zinc is oxidized, and the cathode is a carbon rod immersed in a moist paste of manganese dioxide that also contains some ammonium chloride, and this manganese dioxide gets reduced to dimanganese trioxide. These two half reactions produce a voltage of about 1.5 volts. So 2 or more of these batteries can be connected in series to produce higher volts. So you're probably familiar with most 1.5 volt type batteries, like your AA and your D batteries. But anyways, this is the reaction that takes place in those types of batteries. So another one, these are the batteries in most automobiles. So most of those are lead acid storage batteries. There are 6 cells producing 2 volts each, and they're all connected in series for a total of 12 volts. Oxidation occurs at the anode, where your lead and sulfate get combined into lead sulfate and produce some electrons. And then the reduction occurs at the cathode, where lead oxide and hydrogen ions and sulfate and those electrons all go and form some lead sulfate solid and liquid water. So yeah, a lot of lead going on in that battery. So both the anode and the cathode are immersed in sulfuric acid in this battery. And as electrical current is drawn from the battery, both the anode and the cathode become coated with lead sulfate solid. So if the battery is run for a long time without recharging, too much lead sulfate develops on the battery and it goes dead. So running electrical current through it in reverse recharges the battery. And so the electrical current has to come from an external source, such as your alternator. So this causes the preceding reactions to occur in reverse, and they convert the lead sulfate solid back into lead solid and lead oxide. So it recharges the battery. So as you use your car battery, it builds up all of these products which are no good. Eventually will lead to the death of your battery, but your alternator, which runs because you're driving your car, will actually create a current and run both of these backwards to recharge your battery. So then coming, full circle back to the fuel cell, if our cars don't run on gasoline, what fuels them? Well, the most promising of these technologies is the fuel cell, which again runs on water. These environmentally friendly supercars are really hard to come by. I think there's a Honda FCX Clarity that was a hydrogen-powered fuel cell car, but I haven't seen any of those on the road. These only have water as a byproduct, as an emission. So you can see here, hydrogen gas comes in, oxygen gas comes in. They're allowed to react together, but before they do so, electrons are transferred through a circuit. That circuit is going to be what runs your car. Those electrons are going to be there running our car. So in the in the hydrogen oxygen fuel cell, these guys form water, and then water is the only product. Now, in order to get these guys, we can actually, because you might be saying, well, that's great, water is the only byproduct, but where do you get all the hydrogen and oxygen from? Well, we get it from water. We actually have a neat way of getting these purified gases from water, and we have tons of water, right? Ocean water. So in a voltaic reaction that we looked at, the spontaneous redox reaction occurs, produces electrical current. In electrolysis, which is cutting with electricity, electrical current is used to drive an otherwise non-spontaneous redox reaction. So if there's a reaction that we can't get to happen spontaneously, we can put in electricity and then it'll happen. An electrochemical cell used for electrolysis is called an electrolytic cell. And so here's that word here. So compare and contrast the types of cells for the hydrogen-oxygen system. We've got hydrogen gas plus oxygen gas makes liquid water. This is spontaneous, produces electricity, and can occur in a voltaic cell. So we can put these two guys together, let them react, they generate electricity. This is what we want to do in the fuel cell in the car. But the one to get hydrogen and oxygen from water is backwards. This one's non-spontaneous, this one takes electricity, and this one only occurs in an electrolytic cell. Now, why would we want to do electrolysis? There are a few reasons. One of the problems associated with the widespread adoption of fuel cells is the scarcity of hydrogen. Where is it all going to come from? Well, I told you, water. Solar or wind-powered electrolytic cells can be used to make hydrogen from water. When the sun is shining or when the wind is blowing, we can be generating hydrogen gas. And then we can convert that hydrogen gas back to water in a fuel cell whenever we need to generate electricity or heat. And hydrogen made this way could be very, very, very cost-effective. As a current passes between the electrodes in water, as electricity passes between electrodes inside liquid water, the liquid water breaks down into hydrogen gas and oxygen gas. So we can get this reaction to happen by running electricity through water. And so you can see at each of those two electrodes, different gases are being generated. One side's generating the oxygen gas, one side's generating the hydrogen gas. Now, as I mentioned, there are other applications to this. Most of the metals found in Earth's crust are actually metal oxides, and converting them to pure metals requires the reduction of the metal. That's a non-spontaneous process because they were oxidized as a spontaneous process. Now we want to reduce them. Electrolysis can be used to produce these metals. Electrolysis can also be used to plate metals onto other metals. Silver can be plated onto another less expensive metal using an electrolytic cell. A silver electrode is placed in a solution containing silver ions. And is this plating? Yeah. Silver solution, silver electrodes, silver ions, object to be plated. It could be whatever, nickel, whatever. You put a negative charge on it, and now all of the positively charged silvers will come and stick to it, and we call that plating. Yeah, it's pretty neat. And then the silver ions are coming from the silver electrode. So if you need, anytime that's where they're coming from. That's how they're being replenished in the water after they go and deposit on that other material. Oxidation or corrosion is an undesirable redox reaction, right? Corrosion of metals. The most common kind of corrosion is the rusting of iron. Rusting is a redox reaction in which iron oxidizes into a more brittle form of a solid. So we've got iron solid, and then eventually in the presence of water too. That's important for iron rusting, is that water is present. We get this iron hydroxide compound. So and it's brittle and falls off, and that's not the case with all corrosion. There's an oxidized form of aluminum that they often use as a coating because it actually gets tougher with oxygen on it. Anyways, the iron hydroxide formed undergoes several reactions to form iron. Iron 3 oxide, Fe2O3, down the road. This is the orange stuff that we're looking at here. But one of the main problems with iron 3 hydroxide is that it crumbles off, right? And it's just, yeah. So often there's something that we can do for that. So we use something called a sacrificial anode. I think I have a picture of it. No, I don't. Sacrificial anode it must be composed of a metal that is above iron on the activity series, and that sacrificial anode just oxidizes in place of iron. So you basically would just have your iron hooked up to something that's a different metal, and you'd have that metal, just kind of running off, and then that metal gets oxidized instead of your iron, because as long as they're touching with each other, the electrons will come from that metal and not your iron. They often do this and then bury it in the ground. If it's not obviously not for like a car or something, but if you have metal on your house or something like that. There's also ways to protect from rusting, like coatings. You can put galvanized nails have a thin layer of zinc, and zinc is more active than iron. It oxidizes in place of iron, and then oxidized zinc is actually not crumbly at all and actually stays on the nail pretty good, kind of like oxidized aluminum gets a little tougher too. Oxidized copper as well doesn't flake off as well. It does change the color, but you can prevent iron from rusting by painting it, but and then of course without water the redox reaction can't happen, but if you have exposed surfaces and moisture in the air, that's what happens. One of the other important redox reactions that we can talk about involves the breathalyzer. Breathalyzers work because of the amount of ethyl alcohol in the breath is proportional to the amount of ethyl alcohol in the bloodstream. And one type of breathalyzer is a fuel cell consisting of 2 platinum electrodes wired to a meter and some electrolyte. At the anode, the ethyl alcohol in the breath is oxidized into acetic acid. At the cathode, do I have the equations? I don't have the equations. At the cathode, oxygen gets reduced, and the amount of electrical current produced depends on the amount of alcohol in the breath. The higher current reveals a higher blood alcohol level. And when you calibrate these correctly, they can be pretty precise when measuring the blood alcohol content. All right. Okay, so I guess that's it. So in review, oxidation is loss of electrons, increase in oxidation state. Reduction is the gain of electrons, decrease in oxidation state. Oxidation states are a fictitious charge assigned to each atom in a compound, but it is useful for calculating whether or not an element is undergoing a change, and usually It's calculated by assigning all bonding electrons in a compound to the most electronegative element. We looked at the activity series, which is a list of metals from easiest to oxidize all the way to the most difficult to oxidize. We looked at batteries, different types. We looked at electrolysis, how we can use current to actually drive a non-spontaneous reaction, and we looked at corrosion a little bit to see just what corrosion is and some of the things that we can do to kind of prevent corrosion. All right, learning objectives. Hopefully these are helpful for you guys, and hopefully this semester hasn't been completely terrible online for you. So congratulations, you made it to the end, and hope to see you guys around.